Hello everyone, and welcome back to On the Spot STEM. Today we'll be doing problem number 13 from the 2019 AIME II. This problem reads, regular octagon A1, A2, A3, A4, A5, A6, A7, A8 is inscribed in a circle of area 1. Point P lies inside the circle so that the region bounded by PA1, PA2, and the minor arc A1, A2 of the circle has area 1/7. While the region bounded by PA3, PA4, and the minor arc A3, A4 of the circle has area 1/9. There is a positive integer n such that the area of the region bounded by PA6, PA7, and the minor arc A6, A7 of the circle is equal to 1/8 minus the square root of 2 over n. Find n. So I took a diagram from AOPS and I put it here. We're actually not going to be using the blue line in this solution, so just disregard it. But basically the diagram shows the areas that we need, and this region is included in PA1, A2, and this region is included in PA3, PA4, and we want to find the area of the green triangle plus the area of this black region. So basically we're only given this information, and we're given the radius of the circle if we can use the area. But there's really nothing else that we're given, and so we have to see what we can do with this given information. And now the radius doesn't really matter, and so it ends up being 1 over the square root of pi anyway, so we just disregard it for now, and if we need to calculate it later, then we will, but we can just pretend like we don't know the radius for now. So basically, we're given that the area of this yellow triangle plus this black region over here is equal to 1/7, and then the area of this other yellow triangle plus this black region is equal to 1/9. And also, the area of these two black regions is always going to be the same, and this is because the polygon is a regular octagon. So this region that is bounded by a side of the octagon and the minor arc connecting those two endpoints will always be the same since it's a regular octagon. So these are all equal, basically. So we can just call the area of this weird region bounded by the minor arc equal to E. We'll call that E. And now the area of PA1, A2 is equal to the area of the triangle PA1, A2, and plus this other black region, which is E, is equal to 1/7. And so the area of PA1, A2 is equal to 1/7 minus E. Similarly, the area of PA3, PA4, PA3, A4 is equal to 1/9 minus E. And given these two areas, we want to find the area of PA6, A7, as well as that black region, which is equal to E. So we want to find the area of PA6, A7 plus E. So now we want to see what we can do given our areas. And basically there are multiple ways to find the area of a triangle. We can use Pick's theorem, we can use 1/2 AB sine C, or we could even use base height over 2, which is the simplest definition. We're obviously not given coordinates, so we can rule out Pick's theorem. We're not really given any angles. We don't know the angles of PA1, A2, or PA3, A4, or PA6, A7 for that matter. And so trying to use angles, and we don't really know the length of the triangle side either, besides just the base. So using 1/2 AB sine C doesn't work. But the only thing which works, and which is the simplest way we can find out the area of a triangle, is actually very useful in this scenario. And that is the area of a triangle is equal to 1/2 times the base times the height. And so this is because this is a regular octagon. That means all of the bases of these three triangles are going to be the same length. And that helps us a lot because we can exploit that in our problem. And so all we have to do is find the height, and then we can solve our problem. So let's draw the height from P to A1, A2, and let's call this X. And let's draw the height from P to A3, A4, and we'll call this Y. And so basically, we have that the area, if we can rewrite this area as A1, A2 times the distance from P to X over 2. and that's equal to the area of PA1, P2, which is 1/7 minus E. And the distance between A1 and A2 is equal to S, which is the side length of the octagon, and I'll just call PX as H1 for now. So S times H1 over 2 is equal to 1/7 minus E. Similarly, if we call PY H2, then we have S times H2 over 2 is equal to 1/9 minus E. And this is because A3, A4 is also equal to S because it's a regular octagon. So we're given these two, and now we want to find the area of PA6, A7 plus E. And basically the area of PA6, A7 is equal to, we can call the distance from P to A5, A6 as H3, and we'll label this point as Z, and this is H3. So we want to find S times H3 over 2 plus E. And notice that given our radius condition or the area condition, we can easily find out the side length of the octagon, and we can find the area of this region E by just subtracting this the area of the triangle from the origin to A1, A2, and then that sector. So we don't have to worry about that. We'll basically only have to worry about finding H3. And also, we can find H1 and H2 given this information because we can find out E and we can find out S. So finding H1 and H2 aren't such a pain. And we basically, because of this, we want to represent H3 as some combination of H1 and H2. Because then we can easily just solve for that and solve our problem. So, how would we do this? How can H3 relate to H1 and H2? Well, we notice that if we take this line and we extend it on and on, that this is also perpendicular to A2, A3. And this is because A2, A3 is parallel to A6, A7 since they're opposite pairs and it's an octagon. So if we call this point, we'll call this point Z2. And so basically, we can call the distance from P to Z2 as H4. And now we can solve for H4 given H1 and H2. And if we find H4, then we can find H3 because the distance from Z to Z2 is basically, this line is parallel to A7, A2. And so this distance from Z to Z2 is equal to the distance from A7 to A2. And the distance from A7 to A2 is equal to, if we can draw altitudes here, then we can dissect it into A8, A1 plus these two lengths, and each of the two smaller lengths is equal to S over root 2, and the bigger length is equal to S. So A7, A2 is basically equal to S plus S over root 2 plus S over root 2, which is S plus S root 2. And this is equal to Z to Z2, which is equal to the length of H3 plus H4. So if we find H4, then we can represent H3 in terms of S and H4. And then we can plug that into here. And so, how would we find H4? Well, we can go back to our idea of constructing triangles. And we see that since this is an octagon, we want to look for 45, 45, 90 triangles. So if we extend A2, A3 both ways, and we extend our PX and PY, let's let the points where they hit A2, A3 again be X2 and Y2. So then, since this is a 45, 45, 90 triangle, and since this is PZ2 is an altitude of A2, A3, that means the triangle of P, Y2, and Z2 is also 45, 45, 90, and consequently, the distance from P to Z2 is equal to the distance from P to Y2 over the square root of 2, because that's just a property of 45, 45, 90 triangles. And so, how do we find the length of PY2? Well, we can break up PY2 as the distance from P to Y plus the distance from Y to Y2. And obviously, PY is equal to h2 as defined earlier. And now we want to find the distance from y to y2. And continuing with our team of 45, 45, 90 triangles, we see that y2 is equal to ya3. And so we just want to find the length of ya3. And if we break up ya3, we can see that this is equal to, since the distance from a2 to py2 is equal to px, we see that ya3 plus the distance from a3 to a2 in that vertical distance is equal to h1. So that means h1 is equal to ya3 plus the distance from a3 to a2 vertically, which is equal to s over root 2. So that means ya3 is equal to h1 minus s over root 2. And we can plug in ya3 as substitute for y2. So that means py2 is equal to h2 plus h1 minus s over root 2. So we wanted py2 over square root of 2 because that's equal to pz2. So we can just put it divided by square root of 2 over here. And this is equal to h2 plus h1 over square root of 2 minus s over 2. And this is equal to h4. Now going back, we have that h3 plus h4 equals s plus s square root of 2. So that means s plus s times the square root of 2 is equal to h3 plus h1 plus h2 over square root of 2 minus s over 2. So h3 is equal to 3s over 2 plus s times the square root of 2 minus h1 plus h2 over the square root of 2. So this is equal to h3. Now let's just go back over here. We want s times h3 over 2 plus e. Let's just plug h3 in. And we see that s times h3 over 2 plus e is equal to 3s squared over 4 plus s squared root 2 over 2 minus f times h1 plus h2 over 2 root 2 plus e. So now we want to find basically s times h1 plus h2 because we can find 3s squared over 4 plus s squared root 2 over 2 pretty easily. And so we go back to our equations that we defined here at the very beginning. And we see that if we add them up, then we can take a factor of s. We have a factor of h1 plus h2 over 2 is equal to 16 over 63 minus 2e. And that means s times h1 plus h2 is equal to 32 over 63 minus 4e. We can plug this back in over here, and all we want is 3s squared over 4 plus s squared root 2 over 2 minus s, or minus 32 over 63 minus 4e over 2 root 2 plus e. This simplifies into 3s squared over 4 plus s squared root 2 over 2 minus 8 root 2 over 63 plus root 2e plus e. And all we have to do is find the value of this, and we can get our answer. So how do we do this? Well, now we can utilize the fact that the area of the circle is 1, but we don't even need that because all of this stuff will eventually cancel out. And so basically we can relate our s terms and our e terms in terms of the radius of the circle, because that would be much easier to do if we convert them to a common thing. So basically, so we can find the value of the radius using law of cosines. And so we have, this is the side length, this is r, and this is the 45-degree angle. And so by the law of cosines, s squared is equal to 2r squared minus r squared root 2. And this is equal to s squared. So we can plug this in over here, and we can see that 3s squared over 4 plus s squared over s squared root 2 over 2 is equal to 6r squared minus 3r squared root 2 over 4 plus r squared root 2 minus r squared. And this simplifies to 2r squared plus r squared root 2 over 4. And then we have a minus 8 root 2 over 63 term, and then plus root 2e plus e. Now we have to find this value, e. So we have that in this sector, we have a radius r, we have s, and then we have e. And so basically, the area of the whole sector is equal to r squared times pi over 8. Yeah, and then the area of the triangle here is equal to r squared root 2 over 4. So the area of E is equal to the area of the whole thing minus the triangle. And so that's equal to r squared pi over 8 minus r squared root 2 over 4. This is equal to E. And so root 2 plus 1 times E, which is this expression, is equal to square root of 2 plus 1 times 4r squared pi over 8 minus 8r squared. This is equal to r squared pi over 8 minus 2r squared root 2 over 8. And so we can simplify this, and we get square root of 2 plus 1 times r squared times pi minus 2 root 2 over 8. And also, since the area of the circle is equal to 1, that means r squared pi is equal to 1. So r squared is equal to 1 over pi. And so we can substitute that back in over here. And we see that it's equal to square root of 2 plus 1 times 1 over pi times pi minus 2 root 2 over 8. This doesn't simplify very well. It simplifies to square root of 2 over 8 plus 1 over 8 minus 2 root 2 over 8 pi, which is equal to, or times root 2 plus 1. And this is equal to square root of 2 plus 1 over 8 minus 4 plus 2 root 2 over 8 pi. So this is equal to square root of 2e plus e. And now we have to add it to 2r squared plus r squared root 2 over 4. And then we have to subtract 8 root 2 over 63. So we add r squared times 2 plus root 2 over 4. And r squared is 1 over pi. So we get 1 over 2 pi plus 1 over, or root 2 pi over 4. Or root 2 over 4 pi. So that's equal to r squared times 2 plus root 2 over 4. And we have to add it to this. And then we subtract 8 root 2 over 63. And that's our final answer. So there's a lot of simplification here. This minus 4 over 8 pi cancel out with this 1 over 2 pi. And then minus root 2 over 4 pi cancel out with this. And so we're left with root 2 over 8 plus 1/8 minus 8 root 2 over 63. And we can combine like terms, and we see that it's equal to root 2 over 8 minus 8 root 2 over 63 plus 1 over 8. And this is equal to negative root 2 over 504 plus 1/8. And this is the area of the region we wanted to find. It's equal to 1 over 8 minus the square root of 2 over 504. And this fits this format. And so n is 504, and we are done. Okay, that was a pretty long problem. Basically, to recap, what we did was we, for each triangle, we dissected it into a height and a base. The bases were the same, and that motivated us to make it the area of the triangle as BH over 2. We represented the other regions as E, and we had to add E to our answer on the end to this green triangle. And then we just created equations with the two heights that we were given, the areas of the triangles for, and then we used that to find the height of the green triangle. Then we put that into our base height over 2 formula. We added that to E. That was a long computation, but it simplified very nicely, and we were left with 1 over 8 minus the square root of 2 over 504, which is the answer we wanted. And so our answer is 504, and we are done. Thank you for watching. If you enjoyed this video, please like and subscribe and share with your friends. If you want us to do any more AIME problems or any more topics, please let us know and we will do them. Thank you.